Hello, everyone. My name is Bishoy Sadek, and today I'm talking about Chapter 9, Section 6. The title of this section is called Defects with Binary Outcomes, and the main focus point is event trees. The outcome of the process is influenced by a set of input variables and environmental variables. Under certain conditions, we get a defective outcome. For now, we assume that the input variables, environmental variables, and the outcome variables just have two discrete values, and they can either be good or defective. And that basically means we're just gonna be focusing on two outcomes of all the examples that we're gonna be doing. And that means it could be either good, defective, and like in other cases, it could be on and off. And this analysis is used in many other areas. It basically analyzes all possible outcomes of certain processes. And for key terms, we only have one, and it's event tree, and it's basically a visual representation of binary outcomes that supports the defect probability calculation by connecting the defects in the process to an overall outcome measure. And the book provides two examples to help explain what binary outcomes are. So the first example is an assembly line example, and I like to call it good all the way. In this example, if we have an error or a defect in any of the steps during a process, the final outcome will be defective. And in order to have a good outcome, we have to have good outcomes in all steps. And this is basically like an assembly line. Like, let's say it's a car manufacturer, and it has 3 steps to manufacture a car. Step 1 is to assemble the body of the car. The second step is to put the engine in the car, and the third step is to install the electronics in the car. So in order to have a good car, a good product, we will have to do good in all 3 steps. So the body of the car needs to be good, the engine needs to be good, the electronics need to be good. But if we have a defect in any of the 3 steps, the final outcome, the final product will be defective. So the example we have here says, in the assembly of a simple component, there are 3 steps that potentially can lead to defects. The first step makes defects in 2% of the cases. The second step makes defects in 5% of the cases. The third makes defects in 3% of the cases. In order for the component to function correctly, all 3 steps have to be carried out correctly. In this case, in order for the component to function correctly, step 1 has to function correctly, and step 2 has to function correctly, and step 3 has to function correctly. So the probability of the component functioning correctly is given by probability of good unit, and that equals the probability of a good outcome in step 1 times the probability of a good outcome in step 2 times the probability of a good outcome in step 3. And since we are giving the probability of the defects, so we will simply do 1 minus the 2%, 1 minus the 5%, 1 minus the 3%. And if we do this simple calculation, we will end up with 0.90, which is 90% good unit. And if we want to know the defect probability, we will just do 100, which is 100% minus the percentage of a good outcome. And we will end up with 0.096. And the second example that we have is the medication delivery example. And I like to call this there is hope. That means if there is an error somewhere in the process, but it gets caught, then we will end up with a good outcome. So if step 1 and step 2 in the process do a mistake, but step 3 catches it, this mistake will be fixed and we will end up with a good outcome, and so on. Because it's basically like a circle. So there is no start and there is no end. As long as the error gets caught, it will be fixed and we will end up with a good outcome. And the example we have here says the pharmacy catches 70% of the mistakes that a doctor might make while writing a prescription. Next, the nurse sometimes double checks the medication with the attending physician, which catches another 80% of the mistakes. Finally, sometimes the patient herself alerts the nurse to the medication problem. However, that only happens in 50% of the cases. The medication example is fundamentally different from the first example. In the medication example, the process was more robust because as long as the medication mistake was caught at any of the 3 steps, the patient would not receive the incorrect medication. Put differently, in order for the effect to happen, all 3 steps would have to make the mistake, and which would happen with a probability of, and now we have the formula for probability defect. So to calculate the probability defect, we will calculate the probability defect at step 1 times the probability of defect at step 2 times the probability defect at step 3. And in that case, we got 70%, 80%, and 50%. So if we do 100% minus 70, we will get 0.3 and so on, 0.2, 0.5. So this is, we have 3% that we will end up with a defective outcome. And if we want to get the probability of ending up with a good outcome, we would simply do 100% minus the 3% and we will get 97%. And this is what event trees look like. So here we have 2 event trees. The one on the left is for the assembly line example. And like I was saying earlier, if we find a defect at any step during the process, so we have 3 steps right here. That's the first step, second step, third step. So if we have one defect at any step of the process, we will end up with a defective outcome. So if we start with a defect, next step also has a defect, third step has a defect, we will end up with a defective outcome. And if we have a defect in the first step, but the second step has a good outcome, and the third step has a good outcome, we will also end up with a defective outcome. And the only way to have a good outcome is to not make any errors at any of the 3 steps. So first step has to have a good outcome, as well as the second step, as well as the third step. And this is the only possible way to end up with a good outcome. But in the other example, like it was mentioned, as long as the error gets caught, we will end up with a good outcome. That's why the probability of ending with a good outcome is much, much higher than the other example, the assembly line example. So for example, if the doctor makes an error, which is the first step, but the nurse or the pharmacy catches the error, and at this step, the error will be fixed. So even if the patient ends with a defective outcome, like let's say she doesn't realize that she's not receiving the correct medication, it will still end up with a good outcome because it was already fixed at the second step. And the only way to have a defective outcome is for all 3 steps, for the pharmacy, for the doctor, for the nurse or the pharmacy, and for the patient, to have defective outcomes. That's the only possible way to get a defective outcome. And the book also provides question so we could test our understanding of how binary trees work and how to calculate the amount of defective outcomes or the probability of defective outcomes. The example says, or the question says, an insurance company hands out flyers which customers leave their contact email so that the insurance company can contact them later. These flyers are transcribed to a computer system. In the data entry operation, the typist reads the handwriting from the flyer. In 90% of the cases, the handwriting is read correctly, and in 0.5% of the cases, the typist makes a mistake and writes something different from what he had read on the flyer. Create an inventory, and what is the probability that the data are entered correctly. So this pretty much follows the assembly line example. So if an error happens somewhere, so if the person who's reading the flyer reads it incorrectly or enter it into the system incorrectly, we will have a defective outcome. So there is no place for error. And let's take a look at the answer. So this is the answer right here. So there are two variables with two outcomes each. And we are dealing, I believe this is a typo from the book. So this is 2 to the power of 2. So we have two processes or two steps in the process, and these two steps will lead to 4 different outcomes. So in order to have a good outcome, like I was saying, the person who's reading the flyer needs to read it correctly and also needs to enter the data correctly into the system. If an error happens somewhere, we will end up with a defective outcome. And to calculate the probability of the data entered correctly, we will do the probability of data read correctly times the data typed correctly. And that will be the 95% times the 0.5%. And that will give us a final result of 0.94% of data being entered correctly into the system.